In this video, we're going to cover section 9.5 on the reduction of alkynes. Now, the term reduction is used to describe the situation in which we are forming more new bonds to carbon with less electronegative atoms. In general, a reduction often implies the formation of new carbon-hydrogen bonds. So if we want to reduce an alkene to an alkane, we saw previously that we can use hydrogen gas in the presence of a metal catalyst, like platinum, as shown in this example. We can carry out the same catalytic hydrogenation of alkynes and reduce the alkyne down to the alkane as well. And this can be carried out in high efficiency, again, using hydrogen gas and some catalytic surface, whether that's platinum, palladium, nickel. There's a large variety of catalysts that are used for this process. Now, in the reduction of alkynes, the alkyne must consume two equivalents of H2, molecular hydrogen. So under these conditions, the cis-alkene that is formed via syn addition, this is rather difficult to isolate. And so in general, we cannot isolate the cis-alkene when we carry out the reaction under these conditions. So if we reduce an alkyne with molecular hydrogen in the presence of a metal catalyst, we are only going to be able to produce or isolate the alkane. It'll be very difficult to control the reaction such that we could isolate the cis-alkene. However, we do have a synthetic strategy that allows us to stop the reaction at this stage. And the trick really is to use a poor catalyst, to use a catalyst that isn't so efficient in reacting with this cis-alkene. And so let's look at that example now. So to carry out this reaction that stops at the cis-alkene, we use what's known as a poison catalyst, or a partially deactivated catalyst that is unable to convert the cis-alkene to the alkane. So you can see in this example, if we start with our alkyne, we're using molecular hydrogen still, but now we're using this partially deactivated or poison catalyst, and that will give us solely the cis-alkene. We won't see any further reduction to the alkane. Now, the most common catalyst, poison catalyst, that's used for this application is known as Lindlar's catalyst. Now, Lindlar's catalyst is a complex mixture of quinoline, palladium, some barium sulfate, methanol. It's not important for you to know the details of it, but it is important to possibly remember the name, that we're using Lindlar's catalyst in particular to carry out this transformation. Now, the stereochemical outcome of this reaction is similar to alkene hydrogenation. If there are two chirality centers that are formed, we will only observe 2 of the 4 possible enantiomers. And that's because of the requirement for syn addition. That requirement of syn addition still applies to this particular reduction from the alkyne to the alkene. So as we saw with catalytic hydrogenation, if we look at the energy diagram for this reaction, we see in this example that Lindlar's catalyst is able to lower the activation energy, increase the rate of the reaction as we go from the alkyne to the alkene. But when we get to the alkene, there is no catalytic effect of Lindlar's catalyst on the transformation to the alkane. So we don't see an increased rate of reaction. In fact, we're pretty much stuck in this minima, and so we end up with the alkene as our only observed product from this reaction. So alkynes can also be reduced to produce a transalkene, but we have to do so under different reaction conditions. And the reaction that is used to carry out this transformation of alkyne to transalkene is known as the dissolving metal reduction. And that comes from the fact that we're using sodium metal that is dissolved in liquid ammonia to carry out this reduction reaction. Now, mechanistically, this reaction involves radicals. And so this is the second example of a radical reaction that we discuss in this course. But I would not test you on the specifics of the reaction mechanism. But we do want to go through it so that it's clear as to why we observe the trans isomer forming for the alkene and not the cis. So to start out, it's important to recognize that sodium metal is used in this reaction. And so sodium metal will prefer to give up its electron in the formation of the sodium cation. And so that becomes the mechanistic basis for this reaction. So let's look at that in more detail. So you can see in this starting mechanism, we have our alkyne, and sodium metal will donate an electron, as will one of the pi electrons from the alkyne, to form a radical anion intermediate. And so we can see here that we have a single electron, so we're using these half-barbed arrowheads. A single electron is combining, if you will, with a single electron from one of the pi bonds of the alkyne to give you an anion. The other electron of that same pi bond ends up on the opposite carbon, and because it's not paired up with anything, it is a radical. So we refer to this species as a radical anion. The next step of this reaction, we have a very reactive radical anion species. It's going to react with the solvent, with ammonia. So ammonia is acting as an acid. It's donating a proton in this reaction. And so we form a new carbon-hydrogen bond as a result of those two steps. Nucleophilic attack and proton transfer results in our first carbon-hydrogen bond. Now, in the second two steps, we basically repeat this process where a second sodium atom will donate its electron to the half-filled orbital of the other carbon, converting it from a radical to an anion. And then that anion will further react in a proton transfer reaction with ammonia to give the final alkene. And so you can see that we end up with a transalkene, that is, both R groups are on opposite sides of the double bond. And the reason for the trans stereoisomer being predominant, or the only isomer that is formed, has to do with the relative energy of that radical anion species. So shown in the figure below, you can see that we have two possibilities. We could have the radical anion where both the anionic carbon and the radical on the carbon could be on opposite sides with respect to that alkene double bond, or they could be on the same side. However, if they're on the same side of the double bond, there's significant repulsion between those two sets of electrons, or the single electron, I should say, of the radical and the pair of electrons on the anion. So this structure is a much higher energy structure, and so it's unlikely that that will form during our mechanism. The preferred species, the preferred intermediate, the preferred radical anion intermediate, is the lower energy species in which the anion and the radical, the orbitals containing those electrons, are on opposite sides of the double bond. So this is believed to be the reason for the observed outcome, that we only obtain the transalkene in the dissolving metal reduction reaction. So this scheme summarizes the various reagents that we can use to reduce an alkyne and summarizes what we discussed in this section. We can, if we don't want to stop at the alkenyl stage, we can take the alkyne and react it under the exact same conditions that we did for alkene. So catalytic hydrogenation works efficiently for alkynes as it does with alkenes, and the net result is we form the alkane. However, if you wish to start from an alkyne but transform that only to the alkene, you have two options depending upon the type of stereoisomer that you wish to obtain. So if you use diatomic or molecular hydrogen in the presence of Lindlar's catalyst, that poison catalyst, partially deactivated catalyst, you'll obtain the cis alkene. However, if you choose to use sodium metal in the presence of liquid ammonia, the dissolving metal reduction, you'll end up with the trans alkene exclusively. Now, from both of those stages, we could carry out catalytic hydrogenation and we would end up with the alkane. And the last aspect to consider is whether or not we have chiral centers produced in our final products. If there are chiral centers produced, then again, always recall that the mode of addition will be syn addition. And so we'll never obtain a full set, if you will, of enantiomers. We'll only obtain the enantiomers that result from that syn addition. So if you have any questions about the reduction of alkynes, by all means, get in touch with me. Thank you.